Good morning, my dear students. We have seen the various methods of preparation of alcohols and phenols. We have started studying about their physical properties. We have seen the boiling points, and we have even observed that, or we have even revised that when the boiling point of alcohols and phenols are higher as compared to their haloalkanes and haloarenes or the aldehydes or the hydrocarbon and the ethers, and this is what it is because of the strong hydrogen bonding that is found for those alcohols and phenols, and that is why they have higher boiling and melting points. Same way, my dear students, the solubility of alcohol is even in water is even high because of their capacity to make hydrogen bonding with the water molecules. You can see here that an alcohol combines with the three other water molecules easily to be soluble, and that is why many of the alcohols or some of the alcohols are uh, miscible with water in all proportion. We have even seen that the order of a boiling point or solubility, we can write it that hydrogen is less than is ether is greater than hydrogen, aldehyde is greater than ether, and alcohol is greater than aldehyde. So this is how, my dear students, we can understand about the solubility. Now today in this class, we are going to start discussing about the chemical reactions of alcohols and phenols. Alcohols are versatile compounds and they react both as a nucleophile as well as the electrophile. The bond between OH is broken when alcohol reacts as a nucleophile. Please remember, whenever alcohol reacts as a nucleophile, the bond between O and H is broken. So you can see here in this region, my dear students, easily that when alcohol behaves as a nucleophile, alcohol as a nucleophile, this electron present on oxygen, they attack on the carbon with the positive charge, and then you can get an additive product in which the hydrogen is being removed and the, the carbon is added into the alcohol. This is how we can see that alcohol behaves as a nucleophile, and then the nucleophilic reaction takes place into the alcohol. When alcohol reacts as a nucleophile, the bond between oxygen and hydrogen in hydroxyl group of alcohol is being broken. Now, my dear students, we can understand the reactions of alcohol as an electrophile. So, when alcohol wants to behave as an electrophile, my dear students, actually, alcohol behaves as an electrophile when alcohol turns itself into the protonated alcohol. So first alcohol reacts with the H plus and it turns out to be protonated alcohol. This is what it is known as the protonated alcohol, my dear students. And this protonated alcohol is attacked by the nucleophile so that we can get the final product. You can see that RCH2OH is converted to Br, means RCH2Br. So this is a kind of a substitution reaction, which is the electrophilic substitution reaction. So when protonated alcohol reacts as an electrophile, the bond between carbon and oxygen is broken. So remember that when alcohol react as a nucleophile, the bond between oxygen and hydrogen is broken into the alcohol. But when alcohol reacts as an electrophile, the bond between carbon and oxygen is being broken. Based on the cleavage of oxygen, hydrogen and carbon hydrogen bonds, the reaction of alcohol and phenol may be divided into two groups. So reactions of alcohol and phenol can be divided into two groups. Reaction involving the cleavage of oxygen hydrogen bond. So now we are going to study the reaction that involves the cleavage of oxygen-hydrogen bond. First, we should study about the acidity of alcohols and phenols. So let us first look at the reactions with metal. Alcohols and phenols react with active metals. Active metals means more reactive metals, we can say that. So alcohols and phenols react with active metals like sodium, potassium and aluminum to yield corresponding alkoxides or phenoxides and hydrogen gas. You can see here in this reaction, my dear students, that an alcohol reacts with sodium metal to produce sodium alkoxide and hydrogen gas. When any metal reacts with a substance and produce hydrogen gas, we know that it is the characteristics of a metal that when metal reacts with acid, it produces hydrogen gas. So in this manner, we can simply say that alcohols are acidic in nature, and that is why when they react with metal, hydrogen gas is produced. This was the case of the primary alcohol, but if we have tertiary alcohol, like tertiary butyl alcohol, it reacts with aluminium to give us the aluminium tertiary butoxide and hydrogen gas. So you can see that primary, secondary or tertiary alcohol, all these alcohols, they react with metal and produce hydrogen gas. When we look at phenols, my dear students, this phenol reacts with sodium metal to produce sodium phenoxide. Again, in the process of reaction of sodium with the phenol, we get sodium phenoxide and hydrogen gas is being produced. So in addition to this, phenol reacts with the aqueous sodium hydroxide to again form sodium peroxide. That means phenol reacts with base to produce salt and water. The above reaction shows that alcohols and phenols are acidic in nature. In fact, alcohols and phenols are Bronsted acids, that is, they can donate a proton to a stronger base. For example, if you have a stronger base B minus, if you have an alcohol ROH, it simply gives us BH, which is a conjugate acid, and RO, which is a conjugate base. You can even write it as RO minus, which is a conjugate base. Now, acidity of alcohols. The acidic character of alcohol is due to the polar nature of hydroxyl OH bond. An electron releasing group like methyl group or ethyl group increases the electron density on oxygen, tending to decrease the polarity of OH bond. So an electron donating group decreases the polarity of OH bond. This decreases the acid strength. As the polarity of OH bond decreases, the acid strength even decreases. For this reason, the acid strength of alcohol decrease in the following order. If you have RCH2OH, the acidic strength is more. But if you have R2CHOH, the acidic strength is lesser. And if you have R3COH, then the acidic strength is less. That means primary alcohols are more acidic than the secondary alcohols, and secondary alcohols are much more acidic than tertiary alcohols. So alcohols are, however, weaker acid than water. This can be illustrated by the reaction of water with an alkoxide. So let us understand, alcohols are weaker acids than water. You can take a base RO minus, that is alkoxide, and you allow it to react with acid H2O. It gives us the conjugate base ROH and conjugate acid ROH and conjugate base OH minus. This reaction shows that water is better proton donor, that is stronger acid than the alcohol. You can see that in this reaction that alkoxide RO minus reacts with water to give us alcohol. That means alcohol can be easily produced by the reaction, and the reaction moves into the forward direction, and that is why we can say that the water is a better proton donor as compared to alcohols. So alcohols are weaker acids as compared to water. Also in the above reaction, we note that an alkoxide ion is better proton acceptor than hydroxide ion, which suggests that alkoxide are stronger bases. So sodium ethoxide C2H5ONA is a stronger base than sodium hydroxide. Please remember, sodium ethoxide C2H5ONA is stronger base than sodium hydroxide. This is a very important statement, and please remember this. Sodium hydroxide is considered to be a very strong base, but remember that sodium ethoxide is even stronger than sodium hydroxide. Alcohols are Bronsted bases as well. So alcohols are Bronsted bases too. It is due to the presence of unshared electron pair on oxygen which makes them a very good proton acceptors. So this is how, my dear students, we can understand about the acidity of alcohols. Now let's look at the acidity of phenols. The reaction of phenols with metal, example sodium and aluminum, and sodium hydroxide indicate phenols are acidic in nature. The hydroxyl group in phenol is directly attached to the sp2 hybridized carbon. You can, or you are well aware, my dear students, that in phenol we have an aromatic ring, and in aromatic ring all the carbons are sp2 hybridized, and that is why in sp2 hybridized in aromatic ring the sp2 hybridized carbon is bonded to the hydroxyl group, and that is why hydroxyl group in phenol is directly attached to the sp2 hybridized carbon of benzene ring, which acts as an electron withdrawing group. Due to this, the charge distribution in phenol molecule is depicted in its resonance structure, causes the oxygen of OH group to be positive. Now please understand this well, my dear students. It is very much important for you to understand this charge distribution. You can see here we have a phenol. In phenol, oxygen has got two lone pair. One lone pair involves into the resonance with the benzene ring. As the electron involves into the resonance in the benzene ring, oxygen loses its electron pair and turns out to be positively charged. So you can see that in this three particular if you look at only these three resonance structure, you will find that in these three resonance structures, oxygen has got positive charge. Now, my dear students, you must be well aware that oxygen is a electronegative element. It is second most electronegative element, and that is why positive charge on oxygen, this kind of resonance structures are not so stable. They do not contribute back, and that is why these resonance structures where the positive charge is present on oxygen, they are not so stable. Please remember this, that these three resonance structure where we have positive charge on oxygen, they are not so stable, so they do not cause a stability for alcohol. So this positive charge on oxygen actually try to push this hydrogen to go away. This positive charge on oxygen push this hydrogen to go away, and the electron of this OH bond are, are attracted towards this oxygen due to the positive charge present on the resonance structures of phenol. Now let us study. As we can see that three resonance structures, that is resonance structure number 2, 3, 4, are those structures which have positive charge on oxygen, which makes oxygen to lose H plus ion easily. So due to the positive charge on oxygen, phenol loses its H plus ion easily. Positive charge on more electronegative oxygen even responsible for less resonance stability of phenol. Thus, phenol easily lose H plus ion to make phenoxide ion. Please remember that the positive charge on the three resonance structures of oxygen pushes this hydrogen to go away, and that is why phenol easily makes phenoxide ion and releases H plus ion, which makes it acidic in nature. You can see now these are the resonance structures of a phenoxide ion. In the resonance structures of phenoxide ion, there is double bond between the carbon of aromatic ring and oxygen, but you cannot see that this oxygen does not get positive charge. So as these five resonance structures obtained for the phenoxide ion, there is no positive charge on oxygen. All these five resonance structures causes the resonance stability for phenoxide ion, and that is why phenoxide ion is much more stable than phenol. Please remember this statement, my dear students, that phenoxide ion is much more stable than phenol. When we look at the resonance structures of phenoxide ions, there is no positive charge on oxygen atom. Thus, all five resonance structures contribute well, and phenoxide ion is resonance stable. Thus, phenoxide ion is more stable than phenol. This is a very important statement. Phenoxide ion, being more stable, does not lose any H plus, but phenol easily loses H plus. What does it indicate? That phenol is more acidic than phenoxide ion. Please remember, phenol is more acidic than phenoxide ion. Why phenol is more acidic than alcohols? Let us try to understand. So we have seen that phenol is more acidic than phenoxide ion. So phenol is acidic in nature, but phenol is more acidic than alcohol. Let us try to understand why phenol is more acidic than alcohol. In phenol, hydroxyl group is attached to the sp2 hybridized carbon of aromatic ring, while in alcohol, hydroxyl group is attached to the sp3 hybridized carbon atom. So you can see that in phenol we have ArOH, in alcohol we have RCH2OH, in phenol we have sp2 carbon bonded with the OH group, but in alcohol we have sp3 carbon bonded with the OH group, my dear students. Ar, that is the aromatic ring, is electron withdrawing group. So aromatic ring attracts the electron of oxygen towards it. That is why it weakens the OH bond. So this oxygen, as the electrons are attracted towards aromatic ring, this the bond or the electron of this bond are more attracted towards oxygen, and that is why this bond weakens. So aromatic ring decreases the electron density present on the oxygen. At the same time, if we look at the alkyl group like methyl group, ethyl group, or the other group, they are the electron donating group. As they are the electron donating group, they try to push electron towards oxygen. As they try to push electron towards oxygen, they increases the electron density on this oxygen of hydroxyl group present into the alcohol. And that is why this oxygen easily keep this electron or this oxygen compared to the phenol attract the shared bond pair of electron less, and that is why the presence of alkyl group makes the OH bond comparatively stronger as compared to the phenol. So you can see here that the in RCH2OH even the electron donating group increases the electron density on oxygen, and this bond become more and more stronger that cannot be easily broken. Now, as OH bond cannot be easily broken, what happens? As this OH bond cannot be easily broken, the acidity decreases. So, because acidity is or acidic character is possible by the removal of H plus ion. The electron density on oxygen of hydroxyl group is increased by the alkyl group, that is R or CH3 or C2H5 group, and electron density on oxygen of hydroxyl group is decreased by the aromatic ring. As the electron density is decreased by the aromatic ring and increased by the alkyl group, now we can easily understand that aromatic group not only decreases the electron density of oxygen on hydroxyl group, but involves the electron in the oxygen, involves the electron present on the oxygen into the resonance that we have seen into the various resonance structures of phenol. So, aromatic group weakens the OH bond, while alkyl group strengthen the OH bond in hydroxyl group, and thus phenols and the reactions of phenol AROH, it gives ERO minus phenoxide ion plus H plus, is easier as compared to RCH2OH that gives RCH2O minus plus H plus. That means H plus can be easily given out by phenol as compared to the H plus given out by the alcohol. Both alcohols and phenols are acidic in nature, but phenols are more acidic than alcohol. Thus, phenols easily release H plus ions as compared to alcohols, and we can say that phenols are more acidic as compared to the alcohols. So, my dear students, it was a it was the discussion about the acidic character of phenols and alcohols, their electrophilic and nucleophilic reactions. Now, my dear students, we are going to study about the acidic characters in substituted phenols. So, let us have a look at this point, my dear students. Acidic characters in the substituted phenols. If phenol is substituted by electron withdrawing group such as nitro group, acidic character is increased. Please remember, this is a very important point. If phenol is substituted by the electron withdrawing group, my dear students, then the acidic character increases. Same way, if phenol in the increase in acidic strength is more pronounced when group like nitro group are present at ortho and para position. So the electron withdrawing group are present in ortho and para position increases the acidic character much more. But if electron donating group is present on meta position, it does not increases the acidic character much. And that is why, my dear students, you can see here that only phenol is less increasing order of acidic character. Only phenol is less acidic than metanitrophenol, but metanitrophenol is less acidic than orthonitrophenol, and orthonitrophenol is less acidic than paranitrophenol. Now, one question arises that why orthonitrophenol is less acidic than paranitrophenol? The reason is the in the space when two group OH and NO2 they are placed together, they have steric hindrance, and that is why paranitrophenol is more stable than orthonitrophenol, and that is why paranitrophenol is more acidic than orthonitrophenol. The greater the pKa value, weaker is the acid. So you can see here the pKa value of a phenol is 10. As the pKa value decreases, the acidic character increases. So you